So here's the question we're going to focus on today. Suppose I've got a triangle-free graph with n vertices. How big must alpha be? Alpha of g. So alpha of g, remember, is the max size independent maximum size of an independent set. Independent set. So in other words, we want to prove a lower bound that it's at least something. So now we're in the world of triangle-free graphs. So this thing about alpha being at least delta, this now becomes relevant because if I have a triangle-free graph, as you know from assignment 3, I think everybody got it right. If not, then it was almost everybody, that if you take the neighborhood of a vertex in a triangle-free graph, that's an independent set. So certainly alpha of g is at least delta of g, but we want to do something kind of better than that, because if delta is small, then that doesn't tell you much. Right, so can anyone see why this is true? So I've got a triangle-free graph with n vertices, and I claim that it's at least the maximum of the maximum degree, or basically n over the maximum degree. So actually, technically, I have to put n over the maximum degree plus 1. So actually, this maximum is kind of hiding the fact. I'm writing this as one inequality, but really, this maximum means I'm writing two inequalities. That alpha is at least delta, which we know that's from the assignment. But can anyone see why this one's true? Yeah, exactly. The thing about the chromatic number, it's kind of combining two of these things. So alpha. So I'm going to just write, rather than writing g every time, I'll just write alpha. I hope that's okay. So alpha is at least n over chi because of, by pigeonhole, if I take a coloring with chi colors, the biggest color class has to have at least n over chi vertices. Chi is at least, or chi is at most delta plus 1. So thinking about how the inequalities go, this is at least n over delta plus 1. So this bound, I kind of used the fact that the graph is triangle free. So that was kind of specific to triangle free graphs, but this is actually a bound that holds for all graphs, right? And if you kind of optimize this in terms of the value of delta, like if you think about all the choices for delta and you try to make this lower bound as bad as, if you try to minimize the right-hand side, you'll see that it's about something like square root n, or a little bit smaller than square root n. So we want to get a better, so what we're going to try to do is do something more clever than this to get a lower bound on alpha, which is better than this lower bound. And in particular, I want to say that alpha is like significantly bigger than square root of n. But anyways, basically we want to improve this bound, right? So this is just what I said. And yeah, if you take this right-hand side and see what does it give you in terms of n, you want to minimize this as a function of delta, or take delta and try to minimize this right-hand side. And if you do that, it gives you roughly something like alpha at least like square root n minus a constant, maybe minus a half, but this is a bit imprecise. Okay, so this gives us a lower bound on the size of an independent set in a triangle-free graph, and we want to do something better. Okay, so what we're going to do is try to actually just improve this this bound here. So this delta, or n over delta plus 1. So you might think that the natural thing to do is to try to, actually both of these bounds were a bit silly, right? Actually, people asked me on assignment 3, are you sure that you wanted to ask that question, because it was so easy, like question 1 about showing that alpha is at least delta of g in a triangle-free graph, right? So it would seem like you should be able to improve this, and you should be able to improve the coloring, the bound using the coloring as well. In some sense, we're actually going to focus mainly on this one, trying to improve this. And by doing that, we're actually going to get the best bound that anyone knows on the independence number of a triangle-free graph. So we want to replace this by a bigger function. So we want to make this bigger. Replace that with something large. We're not going to be able to do very much about this one, weirdly enough. If we can improve both of them, then it's even better, but we won't be able to. Okay, so the bound we're going to prove is in terms of, actually, instead of the maximum degree, we're going to deal with the average degree, which it's going to work out nicely in certain ways. So the average degree, of course, is just, so I'm going to call it d. So d is the average degree in G. And of course, to compute the average degree, you just sum up the degrees and you divide by n, right? But by handshaking, there's a much simpler formula for the sum for the average degree, right? So this is just by the handshaking lemma. If I add up all the degrees, I just get 2 times the number of edges. So this is going to be our aim. So I want to prove a bound of the form alpha g at least f of d, where d is this average degree, times n, where preferably, or well, I mean, eventually we'll see, we're going to want that, we want f of d to be bigger than basically 1 over d, because if it was just 1 over d plus 1, we wouldn't have any real improvement here. And if f of d is a lot bigger than 1 over d plus 1, we're going to have an improved bound. So it's going to be better than what we did here, if that makes any sense. Are there any questions at this point? I haven't really done anything. I'm just trying to say what we're trying to prove. And it would be nice if okay. So when I was trying to come up with how to present this, originally I was going to write down the function f, but it's kind of a weird function. And what I would rather do is kind of, just kind of mention some properties of this function f, and then go through the proof, essentially, go through the method of finding a big independent set. And then by the end, we'll kind of see, okay, we want f to satisfy some condition, and this is the function that satisfies that condition. And so the function f is kind of going to arise naturally from the proof. Here's one thing. So I can say that in order for this to make sense, f of d should be decreasing with d. So this is just a kind of comment. So why is that a natural thing? So I'm saying as the average degree goes up, yeah, exactly. Kind of as your average degree goes up, you have more edges. And then naturally, if you've got more edges, it's going to be harder to lower bound the independence number because the independence number will go down. Exactly. So if you've got a lot of edges, then you probably have a low independence number. So f of d is going to be decreasing as a function of d. And that's going to come in because we're going to look at the derivative at some point, and we can say it's negative. So, okay. So that's the first condition we're going to assume about f, is that it's just decreasing. So this is kind of an open-ended question, but so my question is, if I was going to greedily build an independent set, what is the simplest algorithm you can think of? And yeah, that's a bit of an open-ended question. It's kind of hard to answer. Potentially. The thing is, I don't even need to do any kind of local thing. Oh, well, that's a good idea. But we're not actually going to do that. But that makes sense to start with low degree vertices. We're not actually even going to do that. But that actually, in some sense, it would be smart to bias your strategy towards low degree vertices, though. But here's the thing. And why is that a good strategy? Because if I take that vertex with low degree, what that does is so I've chosen it, and it kind of rules out the neighbors. It means now these ones are blocked, right? You can't take them, right? And then if I was doing this greedily, I would just say, okay, delete all this stuff, delete the vertex I chose, delete its neighbors, and just keep doing this algorithm. Just maybe pick a low degree vertex or pick any vertex. I don't really, if you're not being careful, just pick another vertex, delete the vertex, delete the neighbors, and keep going. And the vertices that you've picked at the end will be your independent set. So yeah, so picking the low degree vertices is actually more clever than what I was even searching for in the answer. Just pick a vertex, delete the neighbors, keep going. Well, yeah, that's sometimes, yeah, picking the neighborhood of a high degree vertex is good too. But no, I was really just thinking, pick any old vertex, put it in the independent set, throw it away, throw its neighbors away, and then recurse on the remaining graph. So I didn't have anything more clever than that in mind. But yeah, if you could use this high degree vertex to your advantage, that would even be a smarter algorithm. But we're not even going to do that. So all I'm going to do is pick a vertex, put it into the independent set, throw away the vertex and the neighbors, and then just repeat that on the remaining graph until there's no vertices left. So this is a natural approach. It seems a bit silly, obviously. And in the worst case, this is going to be terrible, right? Even on a triangle-free graph, this is going to be terrible in the worst case. Well, maybe not if I bias towards small degree vertices, then it could be better. But let's suppose I just do it arbitrarily. Then if my graph is just a star, and if I'm just blind and I just pick X as my first vertex, I add it to the independent set, I delete X, I delete the neighbors, I've deleted everything. So if I'm not smart about how I implement this algorithm, I could just end up with an independent set of size 1. Even though if I made a better choice, if I chose here, I would delete this vertex and the neighbor, I'd have an independent set left over, and I would just keep picking from that independent set, and I would have a huge independent set. So basically, instead of analyzing the worst case performance of this algorithm, what I want to kind of think about is what's the sort of average performance of this algorithm. Maybe for the first vertex, we'll see. Well, it's maybe more complicated than that. Well, actually, I hope it's not n over d, because basically that's kind of the lower bound I had before. I had something, I could already do a lower bound of n over delta plus 1, which is kind of, if I ended up with n over d, I'd be a bit bummed out because it didn't really beat what I had before. It's kind of the same. So I want to do something which is more like log d. So this is kind of, so you're not supposed to really know where this log comes from yet, but that's going to come at the end. I want to sort of end up with something like this, which will be an actual improvement. So, right, so this is what I want to analyze, is the average case of the algorithm if I make random choices at every step. So instead of picking just the worst case vertex in every step what I'm going to do is I look at all the vertices I have left, I pick one uniformly at random, so every vertex has probability 1 over n of being chosen, and I kind of keep implementing my algorithm with respect to this random choice at every step. So I throw it away, throw the neighbors away, then I look at what's left, I pick a random vertex, throw it away, throw the neighbors away, and repeat until there's nothing left. So the tricky part is now how to analyze this algorithm, but there's nothing more clever in the algorithm than this. This is all we're going to do is random, greedy choices. And we're not even going to do anything smart like biasing towards small degree vertices or anything. We're just going to pick completely random. Pick a vertex out of a hat. So is this clear? Are there any questions about this? It's not going to be that bad for stars because I think, so we're not going to take a random choice and then think of the worst random choice. So with a star, with probability n minus 1 over n, in the first choice, I pick a leaf. So that's the probability of a leaf. And whenever I pick a leaf, I'm going to get n minus 1 as my independent set. And then I've got a 1 over n chance of picking the wrong vertex, the center. And that time I get 1. But on average, it's going to be sort of a roughly, a little bit less than n. So it's going to be actually quite good on a star. Yeah, it'd be highly unlikely to pick X. Yeah. So it's kind of, this will be whatever, it's n minus 1 squared over n plus 1 over n. It's something like n, kind of. So it's actually really good on a star. Okay, so we're probably going to have to continue this next time. But I only have 2 things planned for the 3 lectures this week. So we're going to kind of maybe spread them out over 3. Okay, so, right. So we're making these random choices. Suppose that if you don't pick X, then you end up deleting X. Yeah, exactly. If you manage to not pick X in the star, then you're golden. Like, it's literally, your algorithm will just go through and pick all the leaves, which is going to be brilliant. So you'll get n minus 1 in the end if you don't pick the star or the center. Okay, so let's suppose I know somehow I've already done the first choice and I chose vertex V. So assuming I've already chosen vertex V, then under that assumption that I've already chosen V, the average size of the independent set produced is going to be, in the end, is going to be 1 plus the average size that you get in G sub V, where G sub V is the graph you get from G by deleting V and the neighborhood. So the 1 accounts for the fact that I've chosen V. So V contributes 1 to the independent set. And then whatever the algorithm gives me in G sub V is, on average, will be like the average size of the rest of the independent set. So here G sub V is, G, but you delete V and the neighbors, right? So is this clear? So this is how you can compute the average kind of recursively. So for every vertex, the average can be computed in that way, and every vertex is chosen with probability 1 over n. So this gives us a kind of formula for the average size of an independent set you get overall, because it's going to be 1, like a kind of recursive formula. So it's like you have 1 from the first vertex you choose, and then you're going to have, for every vertex v, there's a 1 over n chance. So maybe if you think of this as being inside the sum, it doesn't matter. But if you think of this as being inside the sum, it's like 1 over n is the probability that v was chosen. And then assuming that v was chosen, the average size that you get of the rest of the set is going to be the average size you would get if you ran the algorithm in GV, where GV again is G minus V in the neighborhood. Okay, so we've got this expression. So this is the average size of the independent set you get. And I want to show that this is at least f of d times n for some function f of d. Now, inductively, so okay, I haven't told you what f is, so we'll get to that later, but inductively, whatever this f is, if I'm doing a sort of inductive proof, I can assume that the value in this sum, like this thing for g of v, I can assume that this is at least f d sub v times the number of vertices in g of v, where d sub v is the average degree of gv. So d sub v is not the degree of v. That's kind of annoying notation in this. So the degree of v is going to be deg of v. So dv is just the average degree of g sub v. So inductively, I can assume that all of these are at least this value. So I can just plug that in. Right. So the average size I get for in this algorithm on g is at least 1 plus sum over all v and vg. Oh, f of dv. And I forgot a 1 over n here. There should be a 1 over n. Okay, so what are these numbers here? So what's how big is gv, first of all? So almost. So you also have to remember that you're also deleting v. But yeah, that's basically. So if the number of vertices in g, I'll just always write it as n. So it's n minus the degree of v minus 1 to account for v. Okay, so what's the average degree of gv? Well, it's the sum of the degrees of vertices in that graph over the number of vertices. We computed the number of vertices already, so I'll put that on the bottom. And now the sum of the degrees is equal to the number of edges times 2. And we know how, well, let's suppose we know how many edges, or if we write this in terms of the number of edges of g, how many edges does gv have? And if you think about it, so this picture kind of illustrates it. It's like, okay, you could try to say, okay, I delete v, so I lose degree of v edges, and then each of these I lose their degree minus 1. But it's kind of cleaner to think about it this way, that for each vertex here, in the neighborhood of v, I lost all the edges incident to that vertex. And here's the thing, in any old graph, this would double count. So what I want to write here is u in the neighborhood of v, degree of u, where here I mean in g, degree in g. So I want to say that how many edges I lost by deleting v and its neighbors is just the sum of the degrees of the neighbors. Usually in a graph that wouldn't be true, because I could count some of these edges twice. If you had v, you had a neighbor, and if they're adjacent, right? But there's no triangles. So this is actually equality, right? This counts every edge that got deleted gets counted exactly once in this thing, right? Because there are no triangles. So here we're kind of subtly using the fact that, to get this expression, we're using that g is triangle free. Okay, so that tells me what d of v is and v of g, the number of vertices in gv is. Of course, it's kind of annoying that I've got this function here, this f, because if I haven't told you what f is, I can't really compute this. But we're not going to compute it. We're going to kind of manipulate it first anyway. So I'm going to make another assumption about the function f. So at the end, we just have to show that the f we choose actually has that property. But I'm going to assume that f is convex. And the reason I want to make that assumption is because I've got this thing here, this f of dv, which is really annoying, and I don't know what to do with it. If it had an f of d somewhere, I like f of d because that's the lower bound I'm trying to get. I'm trying to get f of d times n. But I've got f of dv, and that differs for every vertex v, and that's confusing. So I want to assume that f is convex, and by assuming that, I'm going to be able to prove some kind of inequality involving this thing to make it look more like So I'm going to make it look more like an f of d. So I want to replace this with something that is just involving d, not dv, basically. Although I won't completely be able to do that, but we'll see what happens. So why does convexity help? So here's a thing about, here's a kind of, this is equivalent to the definition of convex functions we've talked about before. But here's another way of thinking of convexity. So a function is convex if I take at any point, so imagine it's a differentiable function, it's convex if at every point, if I take a tangent line at that point, so like in this picture, taking a tangent line, the tangent line lies completely below the curve. So a thing to think about is like, if you're ever wondering about how things work for convex functions, think of y equals x squared, right? This is the graph everyone has in mind, right? Like, in school, I guess you did so many things involving parabolas that, and yeah, here, anywhere you take a tangent line, it ends up lying completely below the curve, except at the point where it touches. So what does this mean in terms of my f of dv? So we said a function is convex if the tangent line at every point lies below the curve. And if I take I think about the tangent line at the value d. So d, again, remember that's the average degree of the graph. And I think of at a different value of, so at the point, if I evaluate f at dv, if I evaluate the tangent line at dv, it should be below the function at dv. And that, it doesn't matter whether dv is less than d or bigger than d, this should hold no matter what. So this thing is just taking the tangent line at x equals d, so just taking this line and evaluating it at x equals dv. And because we know that the tangent line lies below the curve, we know that this is at most the value of f. And here I've got like the derivative in this, right? So this is how you compute tangent lines, right? It's like evaluate the function at d, take the derivative at d, and then like kind of extrapolate from there with a dv minus d. Does this make sense? Okay. Yeah, it's quite cool. So there's good things and bad things about this. The good thing is that we've kind of taken the d of v out of the f. Like we've got it just sitting here. And this is easier to deal with than having it inside of the f. Perhaps a negative thing you might think is that we've got an f prime of d, and we have to understand the derivative now. But actually we're not, things are going to cancel really beautifully. We're going to end up with some simple formula involving the derivative and f, and it's not going to be that bad. So the kind of great thing about assuming convexity here is we could take out the d of v in some sense. Okay, so if we go back to the expression we had, which was this one. So what I'm saying is this thing in the yellow box can be lower bounded, which is great because that's what we want to do. So we lower bound that by this thing. Okay, and now actually so much of the proof now is like algebra and kind of bookkeeping, which isn't that fun, but let's think about it. So, okay, so this is what we had before we did the convexity thing, and we can say that we can lower bound it like this. So this is just this tangent curve thing. So this, the purple here is at least the purple there, so I can lower bound the whole thing like that. By the way, this is the number of vertices in GV. That's where that comes from. Okay, remember the annoying thing was this dv. So let's separate the stuff that involves dv from the rest of the stuff. So dv, remember, is the average degree in GV. GV is what you get from deleting v and the neighbors. Okay, so if we separate it, so dv gets multiplied by f prime of d and this, basically. And there's still this 1 over n in front of everything. So that's where I get this sum. So this is all the stuff involving dv, and this is all the other junk. And if you do the multiplying out, you'll see that that's correct, I guess. It's either correct now or it's going to be, there's typos which will fix themselves later, but we'll see. If I want to, so let's focus on this one here, the stuff that doesn't involve dv, and I can simplify that quite a bit. So how did I do this? Because I know what the sum of the degrees are in G. If I sum up the degrees, of course that's twice the number of edges, but I don't want to write it that way. I want to say it's, if I sum the degrees, it's n times the average degree. So it's nd, because if I divide by n, that's the definition of the average degree. And each of these coefficients is the same for every v, right? There's no dependent, the only dependence on v is here in the degree. So if I sum over all v, that's just going to replace this degree thing with an n times d. And it's kind of like multiplying this by n because I've got n vertices I'm summing over. So I've got this 1 over n that was there from before times this thing here, which is this could be pulled right out of the sum. It doesn't matter. I've got n squared minus nd minus n. So this gets multiplied by n because I've got n terms. So that's where the n squared and the n come from. And then the n's cancel, some of the n's cancel. So I've got this 1 over n, which cancels. I've got a common n here. So I just get f of d minus f prime of d times n minus d minus 1. Okay, like I said, this is just algebra. If you sat down and stared at it, you can do this, but it's not very exciting. But yeah, so this simplifies this first term, which doesn't have the dv. Now we want to work on this one. Okay, and the good thing here is that the dv is outside of the function here. And there's lots of other good things here as well. So, right, so remember we came up with this formula for d of v, which was n times d minus the sum of the degrees of the neighbors of v divided by, so this is supposed to be the number of vertices in GV, which is that. And the cool thing is I've got this thing here in that sum, right? So this is just copied from the previous slide, right? So I'm not lying when I say that thing is there. And so these just cancel, right? If I plug in my formula for dv, the n minus degree of v minus 1 cancels. So I'm just left with the numerator times f prime of d, and that doesn't depend on v, so it can be taken outside the sum. And so I've just got this. And even that's like mostly pretty simple because it's just, n times d, and I added up n times, so I can kind of pull that part out, which I've got here. And what I'm left to try to compute is this. So this is the sum over all v, the sum over all neighbors of v, and then I compute the degree of u. So I pick a vertex v, I pick a neighbor, and then I compute its degree. So what is this counting? That would be quite a large thing. I don't think it's something that big. Yeah, because, so you can think of, so this thing is kind of counting, it's counting walks of length 2, and another way of saying it. And so it's counting walks of length 2 by picking this vertex first, and then picking that one to be a neighbor of it. So this is like v, and this would be u. And then when I compute the degree of u, it's counting all the neighbors of v. So it's counting walks of length 2. And as was, suggested, another way to count walks of length 2 is to just pick the middle vertex first and then choose 2 neighbors. So it's also counting homomorphisms from P3 into G or whatever you want. And so this is exactly what was the answer given. So thanks for that. So that's, sum of the degrees squared. And with our kind of standard convexity, tricks, we can lower bound this by the sum of the degrees and then squared times 1 over n. And we know what the sum of the degrees are in terms of the average degree, right? Sum of the degrees is just n times d, because by definition of d is just sum of the degrees over n. So here we've got a lower bound. So we are throwing a little bit away here. But if you throw a little bit away, you get nd squared, which is just a simple thing. Now here's the thing. I want to plug this in here. And I want to plug it in for this expression. I've got a lower bound on this expression. I've got a minus sign here. And I want to get a lower bound on this whole thing. And the good thing is I've got a minus here. I know that the derivative of f is negative. So the kind of coefficient here in total is positive because f prime is negative. So if I lower bound this sum, I plug in the lower bound, that gives me a lower bound for everything. Because even though there's a negative sign here, the coefficient is positive because f prime is negative. So that's kind of what I'm trying to say here at the bottom. So actually, I think I can actually finish this in these last 2 minutes. So putting it all together, like you would get this lower bound. So this is just plugging in the, nd squared or whatever it was. If I kind of separate, so I've got an f of d here. I've got an n here. This is what my goal was. My goal was a lower bound of f of d times n. So pull out your f of d times n and take all the rest of the junk and put it over there separately. And I want this to be, so I've proven a lower bound of f of d times n plus this junk. if that junk was non-negative, I'd be happy because it's f of d plus a non-negative number. And this is all just an equate, like it's kind of all just, so I'm actually going to pick f so that this value, this function, this thing is zero. This expression is zero, which is just like taking f to be the solution to some differential equation. So this is just a first order. So if I write this thing equals zero, that's just a first order differential equation. It's not a terribly, I don't know how to solve it, but I don't do differential equations. It's probably not a hard one to solve. I just, ask the computer to do it or ask somebody else what the answer is. But the answer turns out to be like this. It's basically x ln x. So ln is the natural log, minus x plus 1 over x minus 1 squared. And then you have to put in these values because, it's not defined everywhere. Because if x is 1, then, but basically it looks like it's this function here, which you can see is a convex function. Okay, so maybe I'll stop there. I might start next time by kind of finishing this off kind of solidly, but basically what we've proven is that the independent set is at least f of d times n, where f is this function. And this function is sort of like log d over d, because there's kind of a d here, log d over d squared kind of. So it's kind of like d log d over d squared or log d over d. But by the way, of course, if you take a differential equation, there's not a unique solution, right? Because if you add a constant, right, you need initial conditions. But the natural initial conditions here is to take f of 0 to be 1. Because if you have a graph with average degree 0, then you have an independent set of size 1 times n, which is, so that's kind of the right initial condition for the differential equation. And this turns out to be the solution. One thing I don't know if I emphasized, but this is called Shearer's bound. And so if d grows as a function of n, or like if d is large, basically this function is kind of like, if you take f of d, it's kind of like d log d, minus d minus 1, whatever, but that's smaller than d log d divided by kind of a d squared. So it's kind of like, f of d is asymptotically like d over log d, log d over d, right? Because kind of the d's cancel here. And if you were to optimize this, like to see when is this maximum minimized, so it'll be minimized when d is like basically the same as log d over d times n. And if you kind of plug in, like if you kind of work out where the breakpoint is, where these things, where they are roughly equal, you'll see that it gives you a lower bound of roughly alpha is at least 1 minus little o1 square root of n log n over 2. So this is better than the bound we proved at the beginning last time, which was like